Okay, let's resume our session. We'll start where we left off, which was so we defined a very abstract definition of vector space. So why we did that is very simple, because well, we use a lot of the time we just use very specific example of vector space. Not really, we don't really care about abstract definition. But the reason we do this is because by making and understanding abstract definition, we can extend from just using numbers as a field. For example, there are some cases where a space of functions are vector spaces. So in most of the field we talked about, we usually thought about like number system. Like real number is a vector space in a field, and also what else? Rational numbers, and all of these sets they're also very they work like a field, or vector spaces. But the thing is, there are so many cases where the space of functions can be also vector spaces. So by using abstract definition of vector spaces, what we can do is that we can actually think about a lot of more different spaces where the elements are not just numbers. Element can be a field, element can be a function or some set even. So for example, I put the example here. So example, in using the abstract definition of a vector space, we can actually make a set of continuous function on interval 0, 1, and we can group these elements together, and that is also a vector space. You can check it if you want. So these kind of things also work. So the good thing about abstract definition is that we don't have to have element of vector spaces to be only just numbers. It could be functions, some sort of variables that we can use, which is a lot more convenient in a lot of the cases. Okay, this is just what I said before. So now that we've defined the vector space, we can just say we can play with the elements in the vector space. And as I said, by definition, the name of the element in the vector space is a vector. So vector itself doesn't have a definition. The definition of vector is just that it is just element of a vector space. That's vector. So that's a more rigorous definition. So we cannot call something a vector until we define the space first. After we define the space, we can say that the element is a vector. Okay? And before we go on, so we have a vector space. We want to talk about some more spaces and properties that, if you know, will make your life a lot more easier, which one of them is subspaces. So what is a subspace? It is already given to you by the name. That is basically like a subpart of the space. So we already defined the vector space, right? So what is a subspace? Subspace basically is a subset of a vector space, which itself is also a vector space. So we have a vector space. And you could think of some sort of subset right here. And if this qualifies to be a vector space itself, we call this a subspace, right? So that basically, like, a subspace is a subset of a vector space that also itself is a vector space. So if it has also nice qualities, we call this subspace. So the vector space within a vector space. Okay. There are a lot of because of these facts, we want to show that if the subset of vector space is indeed a subspace, and we can actually do this by just taking 3 properties, which I just wrote down, which is we have to check if the subset has a 0 vector inside. So remember that vector space, we talked about how in a vector space it has to have a 0 element. The 0 is in here. So one of the things you have to check to see whether this subspace or subset is really a subspace, we first have to check that the 0 element is inside here. So if this subspace contains 0 element, if it does, that is one criteria for checking whether it's subspace. But you need 2 more, which is this, which is the vector space inside the vector space has to be also closed under addition and scalar multiplication. For example, what could be a nice example? So we talked about the vector space. For the big vector space, basically, inside the vector space, addition and scalar multiplication, which I denoted by dot, they have to be close, right? So if you do any element, if you add them or multiply them, they have to stay inside the set. But in order to check the subset is also subspace, you have to check 3 things. The first thing was that whether the 0 element is also here inside, actually. And the second thing and the third thing is that when you do multiplication or addition inside here, if it stays inside this small subset instead of going outside, we also call that this is a vector space. And because this is a vector space within some big vector space, we call the smaller one subspace, okay? Well, intuitively, kind of like a case where you, like we talked about last time where there was a field and there's inside is also a field, right? Like real number is a field and rational number is also a field, but it's also inside R, right? Something like that. So similar to the vector space case. So we have a vector space, but there could be also a vector space inside. So there could be like different in size, right? So, yeah. So one of the examples is diagonal matrices. Okay. Now this is where like the power of vector space comes out. Set of all matrices can also be a vector space, if you think about it, because it also holds. Like, think about a matrix space of 2 by 2. So, you write something like, let's A be a set, where a set of all 2 by 2 matrices, where let's say this is just R. And for addition and multiplication, we just think of the normal way how we talked about matrix addition and multiplication case. In that case, you can kind of see that this set is also a vector space, right? Because if you add them, it's still matrix, right? 2 by 2 matrix. And if you do scalar multiplication, which talked about, if we like multiply 4 here, it goes inside here, right? So that's still matrix. So set of all matrices, 2 by 2 matrix is also a vector space. But then what you can have is a subset of A, so B, where this is instead this. Actually, I'm going to talk about what diagonal matrices are later on. But for now, just remember that if a matrix is diagonal, that means that only the diagonal part has elements that is not 0. Okay? And other than that, they're all 0. Okay? So you only care about diagonal elements. Other elements are always going to be 0. So this is like set of all diagonal elements. And you can kind of see that the B is a subset of A, right? Because B is just another example of 2 by 2 matrices. But what you can see is that when you do addition and scalar multiplication, this also is a vector space. So what you're seeing is that A is a bigger vector space, and B is a smaller vector space inside A, okay? So that's like an example of a vector space and a subspace, like this. So very nice example, and also nice example because we can kind of see that vector space is not just about elements. Like matrices can be also a vector space. And in this case, we'll call all these matrix as vectors. So in this case, a matrix becomes a vector, right? Because it's an element of a vector space A. Okay? Any question?
서브스페이스 관련 내용은 안 되긴 한데
네.
동떨어진 질문일 수도 있지만 그 리얼 넘버 시스템도 벡터 스페이스의 일종이라고 볼 수 있나요?
할 수 있냐고요? I mean.
네, 벡터 스페이스의 예시로 리얼 넘버 시스템을 말할 수 있나요? 8개 액시오는 만족하는 거
될 것 같은데요? 되지 않나요? 네. 그러니까 그게 있어요. 그러니까 okay. About field and vector spaces is kind of confusing. R is a field, but you can also define it as a vector space. 그러니까 약간 구분이 있어요. 여기서 한국말로 할게요. 그냥 여담이니까. 그러니까 벡터 스페이스 같은 경우는 기본적으로 우리가 이제 약간 필드랑 완전히 같은 건 아닌데 말한 것처럼 이제 필드랑 벡터 스페이스의 구분이 좀 애매해지는 구간들이 있어요. 특히 이제 그런 원디멘션이나 이렇게 가게 되면은 그 경우에는 이제 경우에 따라서 어떻게 하냐에 달려 있는데 결국 이제 그 조건 성립하면은 다 결국 해당이 되는 거예요. So we can kind of also call R like a field, but it's also a vector space kind of like concept, I think, if I remember correctly. So, because like the definition is always, as long as it just hold the condition, as long as the space holds these conditions, it's gonna all work out, okay? Yeah, so. Like normally when you, so that's why like we kind of usually say like, when we say like vector space, we kind of think about space like Euclidean spaces, like Rn, you know, because Rn is like a tuple, right? So you can add them, and you can have like scalar multiplication concept where you times 4 by, for example, 1, 2, 3, you just get it inside, right? So it's kind of like a vector space concept. But because we said n is, we didn't say n cannot be 1, right? So it could be also 1. So it doesn't really matter much. Although in that case, it would be very trivial because it doesn't really differ from like field as well. So it's, yeah, but it can be a vector space too. Any more questions? All right. So we have a subspace. We're going to talk a bit about linear combination. So what do I mean by linear combination? So right now we define vector spaces and we define, well, elements of a vector space, which is vectors. Now we're going to talk about something called linear combination. So what does that mean? Linear combination basically just means it's like a combination of vectors using scalar multiplication and vector addition. So what does it mean is that, for example, let's suppose we have like some arbitrary number of vectors like u and v, UVW. So we have like a UVW here. And what linear combination means is basically like elements such that we do it like this. So what we can do with these vectors, we can multiply each of them by some scalar, alpha, beta, or gamma. Usually, like and for like notation, usually it's very usually we denote scalar variables as Greek variables like alpha, beta, gamma. When you see those kind of notations, they're usually scalars. And usually for Greek symbols like UVW, like alphabets, usually call them like vectors. Just remember that. So basically, what we're doing is that using some vectors, we're kind of combining them in linear sense, linearly, right? We just multiply them by some scalars, and we then kind of added them, right? We call these sort of equation, not equation, but this sort of combination as linear combination. Okay, this is called linear combination. It's used a lot, and you can kind of see that linear combination is going to be also inside the original vector space, right? Because we only did scalar multiplication. So which means this is, each of them belong to V, right? By definition. And adding them still makes them belong to V. So doing linear combination also shows, kind of promises you that the element is going to be still inside the vector space. And it's a very useful concept to say. So yeah, it's basically expressing vectors as linear combination of each other's, right? And here's some example to give you some thoughts about how it works out. For example, we have two vectors like that, right? Actually, I denoted the vectors as if they look like kind of like a matrix, right? But usually when you have like vectors, you can write them in both ways. You can write it like vertically in the slide, which would be like usually column vectors. Or sometimes you can write them in a horizontal way, then you kind of call them like sometimes row vectors, but they all mean the same thing. It doesn't mean too much in the vector sense, so don't worry about it. So there are two vectors. Then what you can see is that you can make a linear combination of v and w to get some vector u. See there? So basically what you did is that you multiply v by 2 and 계산이 잘못된 것 같은데? 잠시만요. 계산 틀렸는데요? 타이포가 있네요. Sorry about that. There's a typo. So, but I can still calculate it. It's a very easy calculation. So, 맞죠? So, there's a typo. For those watching videos, you shouldn't be 7-2, it should be 5-4, okay? So basically you're adding the variables and then you're getting the output, right? So that's a linear combination of v and w, okay? Sorry about that. There could be some sort of typos in the slides. Just think of it as my mistake and just go on with it, okay? Okay, so we have linear combination, but you might think about why are we using this, really, you know? I mean, I guess it's a very nice thing to like able to say that we can kind of combine them, but where are we going to use them? And there are things to talk about, and one of them is spanning sets. What that means is that, you know, we're talking about vector spaces, so give you some intuition. This is also in the end of the slide, but let me just elaborate. So consider like a vector space where it's R2 space, okay? Like a, so in a graph, it should be like an XY, right? So like something like these sort of, although there should be one in the left and down, right? Like a two-dimensional space. And the problem is like we know that R2 is a vector space, but the problem is because R2 is a very large vector space, it has so many elements inside. We want to see if there's a way we can kind of make this vector space using only few elements, because there's so many elements. We want to see if it can be defined by certain qualities, and one of it is by doing linear combination, which we'll come out later on. If you can think about this, for example, think about this. If you get any element here in R2 spaces, it would be like 2, 4, for example. If you have 2, 4, you can think of this actually as a combination of two elements, which is, let me just write on the left side so everyone can see it more clearly. So we have 2, 4, just arbitrary element, and we can make it as a linear combination of two elements, like see? And you can kind of see that the 1, 0 here and 0, 1, they kind of denote like the x-axis and y-axis, right? The 1, 0 is like basically here. Y-axis, 0 is like a y-axis. You can kind of see that using these two elements, you can represent all sort of elements in R2 space, because they can be all represented by some xy coordinates. And this is a very convenient way, because instead of just writing all the elements in the vector space, we can just use two elements and say that actually all the elements in R2 is just a linear combination of these two elements, right? And later on, we're going to call these as these stuff as spaces. Although I'm not going to talk too much about it, but that's the way we're kind of going. That's why we talked about linear combination, because it allows us to talk more about the vector space with just few elements. Okay. So okay, to do that, we have to talk about first spanning sets. So what is spanning sets? Basically, in definition, it's like a set of all linear combination of a given set of vectors. What does that mean? We talk about this. So basically, with some vectors, we can get some infinite number of linear combinations, right? And let's suppose that we gather all these linear combinations into one set. So like we're kind of way, when we say spanning, kind of means that by using these some vectors, we're getting all sort of linear combination we can get. So we're kind of spanning the set with these just two elements, right? So what we would have is that, for example, let's just go for easy cases like in the example. So let's say there's just two vectors uv, right? And let's think about a set where a set is collection of all linear combination of uv, where alpha and beta in this case we'll just say is R, like this. What we are saying is that we're gathering all sort of linear combination of the vectors uv, right? And we're making a set, actually. And in intuition, it kind of shows that the set of vectors can cover some space, right? Like what we did with the 1, 0, and 0, 1. Using 1, 0, and 0, 1, we can use it and combine it to make up the whole R2 spaces. So we're just using some few elements and spanning it to make a space, right? Let me see if I put something here. Yeah, that's the one I talked about, previous slide. The span of plan in R2, right? Oh, I didn't write it. And also, you can kind of do this as an exercise. Linear combination sets like this is also going to be a vector space. You can check out why it works, but they're all going to be a vector space, and you can kind of show it. But like showing something as a vector space or field is a lot more tedious than solving other questions, because when you have to solve something as a vector space, you have to do all sort of 8 conditions that we have to do. So just, I'm not going to solve it here, but you can do it one by one if you want to. But linear combination basically makes up a set, and that set is also a vector space. So this is also a vector space. You can kind of see because it's like all of these span sets are inside, so it's going to be a vector space, right? Any questions until this point? Any questions? Okay. Time for attendance code. This time I'm going to go for 7, okay? All right, moving on. Okay, we have a linear independence now, also related to the concept of linear combination. Now, think about it. So before we talk about definition, let me give you some intuition about what this means really. So for example, we talked about how 0, 1 and 1, 0 can make up R2 space, right? So we had a case where we can make up some point with, actually every point with 4, right? Like this. But then we can think about this. There's actually more than one way to make some elements in R2. For example, like just, what about if I, instead of just spanning the 1, 0 and 0, 1, let's span the R2 with 3 elements. You know, like, why not just, I don't know, span it with this 3. And you can still do it, right? For any element, you can just do it like, for this case, you can do like 0. You can add 0 here to make it. Or for 3, 4, it's even easier. 3, 4, you can do 0, 0, and just 3, 4 to make 3, 4 space, right? You can do this. So you can add more elements sometimes, or maybe sometimes in a way you can take out elements to make more than one spaces, right? In this case, instead of using just 1, 0, 1, 0, 1, we also added 3, 4 and just span the whole set with these 3, and they're going to still span the R. Actually, you can also prove this, but I'm going to leave it as an exercise for you to check it out if you want to. All right? So that's why, but this is a bit problematic because we sometimes want to, because we want to explain some set with some few elements. Now, because we want to be very efficient, we want to think about the whole set by using the smallest amount of element that we can use. So yes, we can explain R2 with these 3 elements, but just using these 2 is easier, more efficient, right? Less elements, and it talks about the same space, right? So how are we going to use this? How are we going to make sure that we're going to find only the necessary elements, right, to explain some space? That is, you can kind of see we don't need 3 elements to explain a space, right? Because if you think about it, you can actually decompose this. Like, let's, what should I do? For example, instead of doing this, let me give some more nice example. So let's just say we just added these 3 all together. It also makes a points in R, right? Which is 4, 5, right? So we got 4, 5, right? Well, you can kind of realize that we can decompose this. This is actually just this. So what we're doing is, even though we can make 3 elements to explain it, we can actually just make this to just say 4, 5 without using 3, 4. And even more, we can kind of see that 3, 4 is actually this, right? You can make 3, 4 from here. And if you just put this here, we get this. So what this shows is that we can actually make sure that we're using the efficient amount of element by telling that if we can make some element out of some elements inside these elements, these vectors, we can show that this is just redundant, right? But just be noted though that it's not that important, but it doesn't have to be these two, right? Actually, you can take this out and use these two, and it still spans the vector space. Doesn't really matter which one you choose. The most important thing is that you just need two elements to explain the space, okay? So, how are we going to write this more rigorously in a mathematical term? So how are we going to say some sort of technique or some concept to say what we're using, like the number of elements we're using are the most efficient number? That is the concept of linear independence. So basically, we say like set of vectors is linearly independent if no vector is a linear combination of the others. For example, again, the example 1, 0, and 0, 1, and 3, 4. We see this is not the most efficient way because we can write 3, 4 as, well, 3 and 4, right? Which means we're writing one element using other elements only, which kind of shows that this is not linearly independent. And actually, we can do it the other way. We can also write like 0, 1 as these two, I think. Let's see. So we can just do that calculation, like, and you would just get so alpha plus 3 beta is 0, 4 beta is 1, so we get 1 over 4, and for alpha you get 3 over 4, right? And remember that if you put this here, you get this, which means you can write this using a combination of this and this as well. But what if, so in this case it's not linearly independent, and for these cases we'll call that the vectors are linearly dependent to each other. Then when does it become linear independent? Take this out, add this too, and imagine if there's a way to make this out of this. Impossible, right? Because even if you do any sort of multiplication, can't make 0 into 1. This doesn't work. So this means that we cannot, in this case, we cannot explain one element using other elements. So in this case, we call that is linearly independent. So we need two elements at least to explain this whole space. So basically that's what we say when it's linearly independent. So what we're trying to do is that intuitively we're using like fewest vectors possible to explain some space, because they can be used, we can combine them to make some other elements in the vector space, right? We used 0, 1 and 1, 1, 1, 0 to explain R, right? So then the question comes up is, well, so we know that it has to be linearly independent to be most efficient, to get the most efficient number of vectors to explain the vector space. And we have chosen the vectors to explain the vector space by spanning them, getting combinations. So how are we going to denote these efficient number of vectors? So we call them as bases, where the basis is simple. So basis is basically a linearly independent set of vectors that span the vector space. Remember that for R2, we saw that 1, 0 and 0, 1 is one of the way to span the set, and it's linearly independent, right? And we put this in some set, right? So these two are the basis for this R, which means we can use them to make up all the elements here. And these are the most efficient number of vectors you can use. So 3, when it becomes 3, it becomes inefficient, right? And the interesting thing is, we saw before that all it matters is just number of vectors. That is, this spans R2. But as I showed you, this also spans R2. And it's linearly independent as well. And I don't know, I mean, 0, 1, 3, 4 also spans a vector space. They all span the same vector space. But there's one thing that doesn't change. Number of vectors. They're all 2, they're all 2, they're all 2, right? So, because the number of vectors for a basis does not change, when we define some vector space, we define them by these numbers. So we call that dimension of the vector space. So when we say a vector space has dimension 1 or 2, we mean it's a number of vectors in a basis. So R2, we will say that is a vector space with 2 dimensions, right? And kind of is intuitively right because R2 basically has X and Y coordinate, which is 2 elements, right? So basically we need 2 elements to just explain that vector space, and we call that the dimension of that vector spaces. And interesting thing is, other things can change, but the dimension, that is the number of vectors in a basis, never changes for a vector space, okay? Any questions? I just wrote down the examples, but for the end, but this is just some same thing. So we can have some vectors, so we're kind of trying to see it more graphically. So we have a vectors 0, 1 and 1, 0. And what they're kind of doing is that they're like spanning the XY plane, right? Using that we can kind of use it as XY coordinates. So like in this case, it's like XY, they're like an XY coordinates where A is the X coordinate, right? And the Y, B is the Y coordinate. We're kind of making it as if like we're doing like an XY coordinate of some elements there, right? And they span the space and form bases. That's why we use them. Yeah, so that's why we use them. Okay, so, and for your information, like even though there are a lot of vector spaces, like those ones where you have this, right? 1, 0, and 0, 1, these sort of ones look like more standard ones, right? That's why we kind of call them like standard bases or sometimes like standard vectors, because they kind of look like the most standard way to like kind of represent the vector basis. So that's another name for them, standard bases. All right. Let's move on. Okay. Okay, we're going to have a short break here because it's the end of the 9th session. And after 10 minutes, we'll move on with the next session.